So in this case, we are going to consider as a continuation, working with an example. Remember, we managed to work with the basics, the notes that we can need as long we are working with the nominal T method. So in this question, we are given, use the nominal T method and calculate the following for a three-phase transmission line. So what we are asked here is the sending end current, the sending end voltage, the sending end power factor, and also the efficiency of the transmission line. So by just looking into this information that we are given, what are we calculating is of the sending end, meaning to say we are or we must be given the information that we must be given here is supposed to be of the receiving end. They will give you a certain information and you're asked to calculate the other side. So meaning to say definitely on this information, it is of the receiving end. But anyways, let us see what we're given. They told us that the line supplies a load of 40 megawatts. It supplies from where we have got the sending and also the receiving side. So where it is supplying is to the receiving end, from to the receiving end. So this power that we are given is of the receiving end. So we are given out of this information, that is the power, okay? As we have got the receiving end side, we have got the power there, which is the true power in megawatts. So we are dealing with what? The true power, which is 40 megawatts at a power factor of 0.8 lagging. So the power factor from where? The receiving end. So this is the power factor of the receiving end, which is of what? 0.8 lagging. So what we can actually do is to calculate the phase angle between voltage and current of what? Of the receiving end, which in this case, we can simply have shift cos 0.8. So already I have fixed my calculator to 3 decimal places. So that was going to give us 36.87. So this is what we are going to have. So meaning to say, as we are going to represent the current from the voltage, remember this is between the current and the voltage, meaning to say wherever we are going to have the current and voltage between that side of the receiving end, we are supposed to consider 36.87, meaning to say, in actual sense, if it is the current, let's say we are dealing with the phase value of the receiving end, it is supposed to be the phase value that we are given there at an angle of this one, negative 36.87. Remember, current, it lags the voltage. We are comparing current from what? From voltage. That is the major case, okay? So that is what we had. And the line voltage is also given on that side of the receiving end. We've got the line voltage 132 kilovolts, all right? So we also have the line voltage on the receiving end, which is 132 kilovolts. Remember, I said we are actually working with a star connection. So in a star, the line voltage, square root of 3 of what? The phase voltage. The phase voltage can be determined from the line voltage over the square root of 3, meaning to say we can take the line voltage, 132 kilovolts, over the square root of 3. So just divide these two. That was going to give us 76.21 in what? In kilovolts. So meaning to say we have got the phase value that is taken from where? From the line voltage, which we actually going to consider. All right, let us just write like this, 76 0.21 kilovolts. We are going to consider the angle for that one. Remember, we are given on the receiving end. These are the values that we are given. So this one will be taken as a reference, meaning to say at what? At 0 degrees. So in this case, we are going to have it later on, meaning to say we can just even write as kilo. That's 76,210 if you multiply by 10 to the exponent of 3 at an angle of what? Of 0 degrees. So you take that one as a reference. This is your step 3. We are taking the information, guys, but as we are taking the information, also do understand your steps. We are going to follow them. Do not worry. But as you can see, we talked about this on step 3. Where we are given the phase value from the given phase value that we are given as the side of the receiving end. We are going to take that one as the reference vector. This is what you're given, meaning to say at what? At 0 degrees. So this is the one that I was just indicating. So we are going to see that one later on. So each conductor has a resistance of 15 ohms each conductor, meaning to say we have got the total phase resistance, that is our total phase resistance, and also an inductive reactance. We are given inductive reactance in this case, but remember what we are dealing with in this case. We are actually working, or we are dealing with what? With the phase values. So this is the total, that is the total inductance that we are given, but as a what? As a phase value of 45 ohms, the one that we are given here, and a capacitive reactance to neutral. Remember, to the neutral. So we are also given the reactance, the total capacitive reactance, which is taken to the neutral. So that is the information that we are given. Remember, I said, as we do follow the steps, we can answer whatever that we are given. The first part is to have the diagram. Yes, we are given here to calculate the sending current, but let's have our diagram, the T method. So remember our diagram, then we can just try to have our questions done. So the first step, guys, is to have your diagram drawn. So the T method, meaning to say we are going to have a T shape. So we're going to have a resistor to an inductor, then across here a capacitor, which is to the neutral. So that is the idea that you're going to have. So on the right-hand side of the receiving end, we also have the same thing, identical to what we had. So we're going to have a resistor and inductor, same properties as what we had before. So that is the major part. So remember, the sending side, this is the receiving end. So that is what we have. We do not have VPS. Okay, no problem. Let us just write the sending end voltage. All right, that's our phase value. Then the current is entering here as IPS. Then in this case, this resistance is the total over 2. You take the total resistance because they are sharing, remember. So we are going to take that RP total. We divide it by 2. All right. Remember from the notes that we had. So this is RP total over what? Over 2. Meaning to say this resistance of 15 divided by 2, that's 7.5. So this was going to give us 7.5 ohms. Also, the reactance here of the inductor, we are going to take the total of it, divide by what? By 2. So 45 divided by 2, that was going to give us 22.5 ohms. So this is the same, these are the same values that you're going to have on the receiving end. So this is 7.5 ohms. This is 22.5 ohms. So that when you combine, you get back the 15. When you combine this, you get back the 45. So this is the same presentation that we are given here, guys. RP total over 2. This is the reactance total over what? Over 2. Then the capacitive part, which is taken between the points. All right, let's have our points. This is A, B, C, D, E, and F. So taken between points B and E, where we've got the capacitor to the neutral. So we have got its reactance. We are given the reactance, the total reactance. This one is not sharing any part with, there is no other capacitor that this only capacitor. So that is the total reactance that we are given of 2,500. And as I said before on the introduction, it's a purely capacitive part that we are given here. We do not have any resistor or any inductor there. So it's just purely capacitive. All right. So that is it, guys. Then to the end, we have got our VPR, in this case, the receiving end voltage, and also the receiving end current, which is the phase value on the receiving end. So just try to have a sketch of the circuit diagram before attempting the questions. So on our questions with the data that we are given, the circuit diagram, let's try to analyze and see how can we determine the sending end current. So the sending end current, if we are to consider properly, guys, it is from this step. I want us to consider the sending end current, supposed to be step number 8, where we have got from this side, calculating of the sending end phase current from our Kirchhoff's law. As we do understand, guys, our Kirchhoff's law from the diagram, sending end current is this one that is entering. So it enters here, another current branches here, another current goes here, which is across the capacitor. So we're going to add these two to obtain that one. So that is very true. That is very, very true, guys. Okay. We are supposed to calculate the sending end phase current from what? From step 8. So meaning to say, from step 8, we have, or we must determine all these back to step 1. Meaning to say, actually back to step 2. Because if you have step 1, the diagram. We are not, guys, they are not going to have a condition where you are given direct. They are not going to do that. Yes, if it is like that, maybe in terms of exam, they try to separate step by step, step by step. But in this case, you can see where you are. This is where we are here. So we need all these steps before step 8 in order for us to reach there. So let's start from where? From step 1 to 8. That is what is going to happen there. So step 1, we had the diagram. Then 2, we are going to determine all impedances that we are given. That is A, B, B, C, and also BE. So let's go back, guys, and determine our impedances. Try to just understand what is happening there. So from step 1, gonna determine the impedances across A, B. Remember, I say this is exactly the same as the impedance across B and C. And thus we've got a resistor and an inductor, R plus JXL. So the resistance 7,5 plus J inductive reactance is already given of 22,5. So this is our N4 electrotechnics. So this is what we have. We can also convert this to polar form, guys, as well. Remember, like I said, that these values, we are going to need them in both formats. So to polar form, let's try and have this one to polar form. So that's shift to polar form. I'm just going to do this one. The rest, guys, I'm just going to write the answers. I talked about this before, how to convert. So you're going to take this one, shift, then this comma here, which is 22.5, then close the bracket. So that will give us the value of R and also the value of what? Of theta. So that is our polar form. R is what? 22,717. 23.717. And also the angle, which is our theta, that's 71.565. Okay. So we also have the angle there. So this is what you're going to do in each and every case where we have a rectangular form. In each and every case, guys, try by all means to convert to the what? To the polar form, so that at least we're not going to have challenges on our calculation to say where we need to add. That's when now you need to convert. It is best that you already convert the two. All right. One to polar, one to rectangular. So that is it about the impedances A, B, and what? And B, C. We also have the impedance between B and E, which is a purely capacitive. So that's ZBE again. All right. So the second one is going to be ZBE between points B and E. This is for the capacitive, this one. It's a purely capacitive. Remember, Z is equal to 0 minus JXC when it is purely capacitive. So meaning to say that's 0 minus J minus a capacitor, guys, you subtract. So our capacitive reactance is what? 2,500. So that's it. We can also convert this one to polar form, just like what we had before from rectangular form to polar form. So already, guys, I showed you how to convert. It was going to give you 2,500 and an angle of negative 90 degrees. So that is it. With the impedances, we are going to use these impedances later on. Follow the steps. You must follow the steps. All right. Number 2 of the steps, what are we going to need? All right. It's actually number 3. Let's say here I'm actually writing as 1. This is the 1 was the circuit diagram. So let's have this one as what? As 2. So let's have this one as 2 so that we maintain the way that we are having there. So the 3 part is having our receiving end phase voltage, the one that we're going to take as a what? As a reference vector, since we have that when we are calculating from the one that we are given. So already we talked about this step 3 here. If you still remember here, we already have that one. So that is already calculated. So that's our step 3 actually here. So this one is already there. Let's move on to 4. To 4, what are we going to? Remember, guys, we need these steps up to 8. Our answer is on step 8. So we're going to follow these up to 8. Using the given load that we have, calculate the what? We are going to need the current there on the receiving end as a phase value. So you work with any suitable formula from what you are given on that receiving end. So let's check according to our information. What are we given on the receiving end? We have the true power. From the true power, we can calculate our value for the current. All right, because we've got the true power. So okay, let me just write it here. So guys, for the sake of space, let me just have my step 4 here. So in order for us to have the receiving end current, we actually do know it is the same as the line current there. Remember, in a star connection. So from the power, you work with what you're given. From what? From the true power that we are given on the receiving end. We do understand under a three-phase true power is equivalent to the square root of 3. We're working with the line voltage as we are given the line voltage there on the receiving end times the line current on the receiving end times the power factor on the receiving end. So as we do need this current, so simply divide, that's the current on the receiving end is going to be power, the true power over square root of 3 times the voltage on the receiving end times its power factor. So that's it. Let us substitute the values that we are given there. So that was going to give us what? Power 40 megawatts times 10 to the exponent of 6. Okay, everything over square root of 3 times the line voltage on the receiving end. We have that one, 132 kilovolts. So that's 132 times 10 to the exponent of 3. The power factor, 0.8. So that's 0.8 there. So that was going to give us what? The current, the line current for the receiving end, which is 218.693 amps. But remember, I said this one and the phase current will be exactly the same. So meaning to say we have got the current there. So that is the idea. So we have got the current at which angle? All right, let's see first here. So we said the current as a phase value on the receiving end is 218.693. Remember what I said, what is happening between the receiving end and what? The receiving end voltage and also current. The phase angle, it is between those, the voltage that we have on the receiving end and also the current that you are having on the receiving end. So if you're dealing with the phase values, it is one and the same thing between voltage and current. So we have got a lagging power factor, current lags voltage. So this current here is lagging the voltage. Remember, the voltage for the receiving is the one that we took at what? At 0 degrees as the reference. So it will be on the reference. Then the current will be on the other way, lagging, having a negative angle. So it's going to take a negative angle, that one. So remember our angle was what? 36.87 degrees. So that's it on that step of finding the receiving end phase current, which we can also do convert this one to a rectangular form. So on your calculator, that was going to give you 174.954 minus J131.216. Remember, I said, guys, try by all means to work with both rectangular and polar form. Try by all means to work with both rectangular and what? And polar form. So that is it on step number 4, determining of what? The receiving end phase current. Then 5, we must calculate the voltage drop occurring between the points B and C, which is what? VBC. Between the points B and C. So meaning to say between points B and C, what are we going to need there? The current and the impedance between points what? B and C. Remember, we've got what? The impedance between B and what? B and C. So that is going to be the current on the receiving end times the impedance there. So that's our step 5. All right. So let us just have the calculation here of our step 5. So these are the steps, guys. Just make sure you follow each up to the one that you need. All right. So on step 5, we are going to need, all right, we are going to need VBC across the branch B and C. So that is the current on the receiving end times the impedance across the points B and what? B and C. All right, the receiving end and the impedance is there. So on the receiving end, the current is the one that we calculated. So we have got this one, the phase value. And yet a product. A product is best to be done in what? In polar form. All these we have in polar form. Remember, this is the one that we have got here. So guys, just take note of the values so that I do not keep on shifting like this. Just take note of the values. We've got this one. And the impedance across B and C is the one that is the same as across A and B is this one that we calculated here. We need this one in polar form. So we're going to take these two, multiply them together. So that is the idea there. Know your formulas. So this is a repetition, guys, of your N4. Remember working with what? Polar form product. So that was going to give us 218,693 at an angle of negative 36,87. Just also verify with your values because here, guys, as you can see, we are working with a lot of values. Then the impedance across BC, we also determine this one in polar form. It gave us 23,717 at an angle of 71,565. Remember, that was it. So that is going to give us impedance across the points BC. Polar form, you multiply these two together. The magnitude there you multiply, that was going to give us 5,186,7242. Then the angles you add the angles. Remember, guys, add the angles. So that was going to give us 34,695 degrees. So we have this, which we can also do convert to a rectangular form, which was going to give us 4,264,507 plus J 2,952,334. So that is it. We have got our answers both all right, presented polar and rectangular form. So that's our step 5, finding of what? The voltage drop across B and C. Then 6, we will need that one across the capacitor, which is simply to be added. We simply have to add if we are working from the smaller voltage to a bigger one. Remember, we are working from smaller to a bigger one. So VC will be the sum. The receiving end phase voltage plus the VBC that we added, that we calculated. And remember, addition, like I said, it is best done in what? In rectangular form. So you must take the receiving end phase voltage and VBC in what? In rectangular form and add them. So that will be our step 6. So already these ones, we have got these values already. So this one is just a continuation, guys. Just follow up as it is. So we have to find VC, which we said VC is equal to VPR plus VBC. So this one, we calculated this one before, guys, and it gave us 76,210 plus J0 in what? Rectangular form. Remember, it is the one that we said we're just going to take it at what? At reference at 0 degrees. Plus our VBC. We also calculated this one. We have got this value in rectangular form. So that's it. So it is just going to be a lot of things, like in terms of maybe you're in exam, you think that there's a lot of things that I'm working with. But those are steps that you can actually follow up. You follow up these steps. You just need to manage how to follow up the steps, but everything will be clear like this, guys. Add in rectangular form. Remember, add the real terms together. So that was going to give us 80,474,507. Then the imaginary part together, the part together, this part of J. So 0 plus this one, guys, as you can see, there is no effect. It's just going to remain as 2,952,334. All right, so this is it. So we have got our voltage across the capacitor, which we can also convert to polar form. From rectangular form, convert to polar form, it was going to give us 80,528,644 at an angle of 2.101 degrees. So make sure, guys, on the calculator there, everything must be done properly. So this can help us to find IC, current across the capacitor. This can, you see, guys, all these steps. What we needed is to find the current across what IC, which is to be added to this one that we calculated on step 4, the current on the receiving end. Remember, this is what we want, this part, and also this one to be added. So that is the importance of all these steps. So to find that current, that's our step 7, the voltage across the capacitor to its impedance across the capacitor, which is what ZBE. Remember, BE is the one across the what? The capacitor. And we add that the impedance BE, right? From this part here, across the capacitor BE. And on the impedances, we have that impedance. We might remember the impedance, this one, BE, in what? In polar form. So divide the two, we have got the currents. So that was the idea in this case of our step 7. We must find the current across the capacitor, which is simply VC over the impedance across the capacitor, which is BE. So taking this 80,528,644 and the angle given, okay, we're going to simply divide to the impedance across the capacitor, which was 2,500 at an angle of what? Negative 90 degrees. Remember, we are dealing with a polar form. Division in polar form, divide these two together. So you must divide those two. That was going to give us 32,211. And the angles we subtract. So it's actually 2,101 minus 90 like this. Minus. So it will end up be a positive. So that will be 92,101. You add at the end. All right, that's 101. So this is the current that we are going to have across the capacitor. All right, current, measured in amperes, which can be written in rectangular form. As we do understand, we are going to add these at the end. So addition best in rectangular form. So convert this one to rectangular form. That was going to give us negative 1,81 plus J32,189. So that is it in a rectangular form. So this is what we need. We're going to take this current that we calculated and that one that we calculated in step 4. Step 4, that was the current that we have on the receiving end, if you still remember here. So these are the two that we need. As we said, from the Kirchhoff's law, guys, the current that we need on the sending side is the sum of what? Of these two currents entered. That is the one that are away from the junction. B is our junction. So we've got this one taken away and also IC taken away. So the sum. So guys, some of these values I'm just going to erase. Make sure that you do remember all these values. So that is the final step for this question A. which is step 8. Like I said, we are going to do everything up to step 8, where we have got the current that we need on the sending side from our Kirchhoff's law. So we're going to take the current on the receiving end plus the current across the capacitor. Sum in rectangular form. So take the values in what? Rectangular form. So that's it. Here we already have our values. Already these ones are there, guys. You've got this one. 17 4,954 minus J 131,216. Okay, so this is it. So what are we going to add? We are going to add the one that we calculated across what? Across the capacitor. So this is the idea of the question. The is the one that we calculated across the capacitor, guys, which was on step 7. All right. So for the sake of your reference from your calculation, this one that we calculated here on step 7. So take this value as it is in rectangular form. All right. So let's combine. As we can see, that one is having a negative there. Just going to open a bracket. All right. So that was negative 1,181 plus J 32,189. So that's it. We combine everything. So that is the sending end value that we are going to have as a phase value. This is the phase current, remember. So the sending end value at the end, adding these, we were going to have, so here, we want to add, take the real terms. So this is this one plus and a minus. Yes, so it's going to be a minus. So it's like 174,9 minus 1,181. You subtract that one. Okay, so that was going to give us 173,773. Then in this case, it's negative this plus this one. Remember, plus and a plus. So that's negative 131.216 plus 32,189. You add those two, that was going to give us a negative at the end. This one was going to give us a negative J99,027. So that's our current on the sending end, our sending end phase current. We can also rewrite this one in polar form. So rewriting this in polar form was going to give us 200,009 at an angle of negative 29,677 degrees. So that's it. That is how we can play around these typical questions. As we can see, there'll be a lot of stages, steps. We have to follow this step after this, you follow this after this. So do not forget the values, guys, that we calculated, because I'm going to erase some of these values. As you can see, we have a lot of things on our information here. So that's A, the sending end current. So we're not done. Move on to B, which is the sending end voltage now. The sending end voltage. We are dealing with the sending end voltage. Like I said, you calculate the phase value, then you can convert that one to the line value or on your final answer. When dealing with voltages, you must convert your final answers to line values. All right. So how can we determine this? If we are to check as part of our steps, we are going to see that This voltage is, okay, if we check from step, actually supposed to be from 9 and 10. If you check properly here, that is where we deal with what? The sending end voltage. Step 9, you must have the voltage across A and B. And since we are working from the smaller voltage going to the sending, going back to what is sending, which is the bigger voltage, the phase value at the sending side is going to be VC plus VAB. So we need VAB. Then we can convert this to the line value, like I said before. So in this case, we do not have VAB. We never calculated the voltage across A and B. We only have the impedance and also the current. Here we said these impedances are the same, but the currents are different. The current on the sending and the current on the receiving, they are different. So therefore, the voltage drops are different. So do not take that one to say, I said the impedance is between A and B and C are exactly the same. So therefore, you also take the voltages. No, do not mistaken that way. All right. But as we do need this voltage, all right, so this will be from step 9. So here we are on now, we are now answering B, but we can work from step 9, calculating the voltage across A and B first. So as we can see, we've got current on the sending side times what? The impedance across the points A and B. So everything is there, guys. We calculated this one before from A. We calculated this one from A, but we need this one in what? In a polar form. So remember, we got 200,009 at an angle of negative 26. It was 29,677 degrees. Then we multiply to the impedance across A and B. Also, we calculated this one. Remember, A and B same as what? B and C. So we have got this impedance, guys. We calculated this one before. It was 23.717 at an angle of, all right, at an angle of 71,565 degrees. This is what we had. So we need the product of the two. So remember your polar form as you are working with a multiplication. Now multiply this one times this one, the magnitude together. So let's multiply. That was going to give us 4,743,613. And the angles you must add product. This is product, guys. So the angles you add negative this and this 71, you add the angles together. So that was going to give us at the end 41,888 degrees. Convert to rectangular form. Since we are to add these later on, so it's best for you to convert to rectangular form. So that when you are to add, you are not going to have any problem there. Okay, so that is what you're going to have in a rectangular form. So later, from this voltage across A and B, remember we just have the voltage across A and B. And what we need is the sending end phase value that you're getting. So we are going to add, because we have got this voltage across A and B, and we have got the voltage across the capacitor. So we are going to add these two. All right. So remember, from a smaller value to a bigger value, you're going to add from a smaller to a bigger value. So the voltage on the sending side, which is the working with the phase value of the sending side is going to be what? VC plus, all right, it's actually, okay, no problem. Anyway, the one that you want to start with, VAB plus VC. So VAB, we already have this value in what? In a rectangular form. Okay, so that is it. So guys, once you just work out these, you won't have any problem. You won't have any problem. Adding the voltage across the capacitor, we had this value, guys. We calculated this one before. Remember, that was 80,474,507 plus J. We had this value. So, guys, you have erased a lot of values. So just make sure you do remember the values that you calculated before. You do remember all the values, okay? Actually, you have written them down. So that is just take from those values. That is what you're going to have in this case. So let us combine and have the sending end voltage, which is the which is the phase value actually that we are dealing. We are dealing with the phase value on the sending end. So adding these together, we were going to obtain a sum of 84,005, 896. We add the part of a J together. So we've got the J part and this J part. Combine those together. That was going to give us 6,119,534. So that is what we're going to have at the end, and the sending side, the sending end. But as we do understand, for us to do convert this to a line value, it is best that we must have this in what? Polar form. So let's have the first value for the sending end in what? In polar form. So convert to polar form. So if we are to convert this one to polar form, it was going to be 84,228,494 at an angle of 4,166 degrees. So that is what we have in what? In polar form. But remember, this is what? A phase value for a voltage. Three phase, you must work with what? You must give your answer as a line value. So meaning to say, we are going to convert this one, remember, under a star, the line voltage, the square root of 3 of what? Of the phase voltage. So therefore, we're going to calculate the line voltage on the sending end. So that's square root of 3 times. Okay, so in this case, we take the magnitude. In polar form, what you take is the magnitude. You work with the magnitude on the multiplication, whatever that you're going to have. So that's 84,228,494. So that's it. We were going to have the line voltage on the sending end. So that was going to give us 154. All right, it's actually 145. This is 14588. Guys, you can even convert this to kilovolts. Divide by 1,000. That was going to give us 145,888 in what? In kilovolts. So that is whenever you are asked to calculate for a voltage, at the end, you must express your answer as a line value. On calculations, within these calculations, those are phase values that you deal with. Within, as you are doing your calculations, but the final answer now, For voltage, you express it what? As a line value. So that is the idea of our question. We are done on this one. Remember, we needed the sending end voltage. The other question, which is on C, it was the sending end power factor. The sending end power factor. So in order for you to have the sending end power factor, remember what I said, guys. We are going to need the phasor diagram. In this case, we are going to need the difference between the phase, between this side that we are given. Sorry, let's go back to the question. The sending end power factor. So we are going to need what is of the sending end from the sending end. So the first thing is that the phase angle of the sending side, it is actually to be taken between the voltage that we have on the sending side and what? And the current that we have on the sending side. That is the idea there. So this is where we are going to need the vector diagram as we had on our step 11. Remember from the introduction part. Taking, as we have got our VPR, the receiving end as the reference, because those were the values that were given, remember? Compare the angles that you're given, then add them together. So if we are to consider that, we can see that from this idea, remember already, we have got, we took the receiving end as our reference. So we have got the receiving end here at what? At 0 degrees as the reference. So the question is, what about the current? If we are to consider IPS, remember IPS, we have got this current here. It's only that I erased some of this information, but here we can see it where we used this current here, IPS. It is at an angle of what? Negative 29,67. The angle there is showing us from where? From the voltage, which is at reference, from 0 degrees. It is at a negative. So negative, that is clockwise. If we are going this way, from this quadrant, from the reference, guys, in this way, those angles will be what? Negative. From the reference at 0 going this way, those angles will be positive. Remember that, guys, from your N4. So that was the case of our current. In this case, it is lagging. It is at a negative angle, 29,677. From what? From 0 degrees from the reference. Negative 29 will be going this way, in between 0 and what? And 90. So that is our sending end current. What about the voltage? Because we are comparing with what? The sending end voltage. So if we check properly, the sending end voltage, we calculated, this is the one that we had here, sending end voltage. Its angle, here, this one, phase value, its angle is what? 4,166 degrees. That is the angle that we are given there, the one that we calculated. Positive, which is what? A positive angle that we are given there. So meaning to say, from the reference, we must going positive from 0 degrees. That's our reference. So this one, it's on the positive side. We are going up. So that's 4,166 degrees. So that is the angle that we have between what? 0 degrees and the what? The sending end voltage. That is what exactly you are given from those angles, guys. That is what those angles represent. This is what these angles represent. So as we need the angle that is between the sending end voltage and sending end current, between these two, sending end voltage, sending end current. So the angle in between is the sum of those two. So that is our phase angle now for the sending end. We must add 4,166 plus, yes, this one we said, writing it, it's a negative in terms of the presentation. But as you combine the angles, the difference, how open this is, you add those angles that you're given. All right. So, all right, no problem. Let me just finish, guys. My body has just affected everything. But in this case, you combine those. So meaning to say our angle at the end was going to be 4,166 plus the 29,677 degrees. So adding, that was going to give us 33,843 degrees, which we can now use to calculate the sending end power factor, because as a power factor that is cos of what? Cos of the angle that is given, cos 33 843 degrees. So that was going to give us the decimal part representing our power factor. So that is how these questions are given as. So that was going to give us 0,831. Remember there, the current was what? Lagging the voltage. Voltage was here. The current was here. So it is what? Lagging. Current lags the what? The voltage. So that is how these questions might be given as. Then the efficiency of the transmission line. So this will be from your the calculation efficiency, guys. We do know this one is direct as a percentage. We said efficiency is going to be taken from what? The output, which is our receiving end, over the input, which is the sending end, times what? 100%. But if we check, we were given already the receiving end, this one we're given already in megawatts. It's already given. What we do not have is of the sending end. As we have been calculating values of the sending end, it means we are also forced to calculate that power on the sending end. So this is part of our step 12. Calculation of what? The sending end power. Remember, 3 phase. So the square root of 3 times the line voltage on the sending end times the line current that we have on the sending end times the power factor that we have on the sending end. So in this case, we've got everything. So remember, on those values that we calculated on the sending end, we calculated the sending end voltage there. So we have got that one. We need the magnitude. In polar form, it was 145,88 in kilovolts. So that's times 10 to the exponent of 3. All right. So there we have got our line voltage. Remember also the sending end current. We calculated this one. That was in polar form, 200, 009 times the power factor. For that in sending end, we also calculated the power factor. That was our part C there, which we got 0,831. So as you can see, this one was just everything that we calculated. So that is it. It was going to give us a value of 41,000. This is actually 41 million, guys. 998,208 watts. Guys, we can convert this one to megawatts, as we have got this one in what? In megawatts. So megawatts, that's times 10 to the exponent of 6. So we divide by 1 million, or we multiply by 10 to the exponent of -6, which was going to be 41,998. So by doing this, multiplying by 10 to the exponent of -6, we are automatically converting our answer to what? To megawatts. So that was our power, this one in what? In megawatts at the end. So this was going to give us 41,998 in what? In megawatts. Same units as you are to deal with the division there, or you can just write anything, then you just remove those times megawatts times 10 to the exponent of 6, any way that you understand. So anyways, substituting these values, remember, receiving end already we are given, that was the 40. So this is 40 megawatts, guys, over what? The sending end also in megawatts. So these are same units, guys. Megawatts is going to cancel. All right, times what? 100%. So that was going to give us the efficiency of what? Of the transmission line, which was going to be 95,243. All right, so as a percentage. So that is how these questions mostly, that is how they are given. You just need to follow the steps. Follow the steps. It does not mean that you are supposed to follow those steps hand in hand to say this one. No. What you understand, calculate what you understand from the given information, from what is missing, like that. You can have even a reverse way of, as long there is information given that can help you to calculate a certain value, use it and calculate that part that is required. So let us do revise as many questions as we can, while as we are preparing for the exams which are ahead of time.